Okay, so today we're going to take a look at vector valued functions. So just some quick review. So there are three functions in one dimension generally relating to particle movement, which is position, velocity, and acceleration, or S of t, v of t, and a of t. Um, the three functions are all related, so v of t equals s prime of t, or the change in position over the change in time, right? How fast are you moving? And then a of t is the same as v prime of t, or the change in velocity over the change in time, or how fast are you gaining speed. So that should hopefully all be review, and of course you can always integrate to go the other way with respect to time. Now, in two dimensions, we have very similar functions, but they just have two dimensions now. So instead of s of t, position is now called r of t. And same thing where velocity and acceleration are the derivatives of position and velocity, respectively. So, how do these vectors kind of interact here? We take the position vector, and that is like so that you go from the origin to some position, and then the velocity vector. So over time, that velocity vector gets added to the position vector to get this new position vector. And just over time, this will happen more and more as the particle moves. Now, similarly, we have this velocity vector, this initial velocity vector, and then the acceleration vector, which is in pink here. And over time, that initial velocity or that acceleration vector will be added to the velocity vector as like the change in velocity to get this new total velocity vector going here. Pick a better color in green. So over time, like you're adding or in other words, yeah, you're adding the small pieces of velocity to the position over time and adding the small pieces of acceleration to the velocity over time. And that this would be the equivalent of saying that a velocity at some t equals the integral from zero, or I should say the velocity at zero plus the integral from zero to t of a, a at, let's say, u du. So just like saying that accumulation of acceleration over time. Um, a unit vector is just it's just an easier way to write these things out. So you'll have I, which is basically the standard unit vector in the x direction, and then j, which is the standard unit vector in the y direction. So this vector, a vector is which this should be review, but it's represented by this form a like these brackets and then a comma b, where a is how far it's traveling in the x direction and b is how far it's traveling in the y direction, and then like that's just the whole vector. Um, by using these I and j, that's basically saying like either a or b equals 1 and the other one equals 0. So how do we use these? That's kind of random, right? So the way we use these is any scalar multiplied by vector is just a scaled vector, or a vector basically made bigger by that scalar. So when we use when we use when we use I and j, we don't need to have these like annoying angle brackets written out. It's just represented implicitly by I and j. So therefore, any number a I is basically the equivalent of saying a comma 0 as a vector, because this I represents 1 comma 0, and then this is just multiplied by a equals this. So that's just an easier way to write it, but don't let it confuse you too much. It's just almost like a placeholder to represent this vector, and that way we can have it in one line as a sum of terms rather than having it written as a separated vector. And we can do more things with functions like this. Um, so we've already done this kind of above, but you can see like v would also equals ai plus bj, because that would just be a times 1 comes 0 plus b, that's the vector 0, 1. And then you would just multiply that together. 0, B, and you're good to go. Like that will sum back to what V initially is. So let's do an example here. So we're going from P to Q. I'll just draw a quick coordinate plane here to kind of make it easier to see. So P is somewhere up here and Q is somewhere over here, and the vector is going to look like that. So the way we get this vector is just do for the x value and the y value go like basically what it is on Q minus what it is on P, because it's from P to Q. So 3 minus -1 equals 4 for the x component, and then for the y component, 2 minus 5 equals -3. So the vector is going to be 4 comma -3, and then in terms of I and j, we just write that as PQ equals 4i minus 3j, and that's what that's going to look like. And so yeah, this function to describe a particle r of t is usually in a vector form. So r of t, later you'll see like a vector symbol being used there, but you don't really need to put it there for now. So that'll be like, you can call it f of t and then g of t as the vector components, but you can also just write this as f of t times I plus g of t times j, just so that we don't need this vector form and it's just written as a linear combination. So the rules of calculus are the same. Once you have it in this linear combination, you can just derive or integrate term by term because it's addition, and the I and j are treated as constants. The only difference is that there's this new concept called speed, which is just the magnitude of velocity. So equals the magnitude of velocity. And what that means is literally how fast is it going. But what it practically means is if, let's say, velocity is this f of t and g of t, to get that magnitude, you just say like the magnitude of velocity of t, and you never write it as a different number. You just write speed represented by the magnitude of velocity. So this would just be equal to the Pythagorean theorem, which is just f of t squared plus g of t squared. And additionally, there's this concept of direction, which is just what's the unit vector where you're going. The way you get that is the unit vector of where, like, what direction you're traveling in. So direction, that is just equal to the velocity of t, that vector value function, over the speed, or the magnitude of velocity of t. So as you can see, if you divide it by the magnitude, if you divide a vector value function by its magnitude is just going to be 1, which makes it a unit vector, and that's a little nicer to work with sometimes, especially when you're working with like sine and cosine and stuff like that. So just remember those two definitions, and you're good to go. So now some examples. To find the velocity and acceleration vectors, you just need to remember that velocity is the derivative of position. And just write it out from there. So that would be -3 sine t times I plus 3 cos t times j. And then acceleration is just the derivative of velocity, which is -3 cos t I minus 3 sine t times j. So those are your two, they're your velocity and acceleration vectors. And then you just need to plug in t equals pi over 4. Luckily, both sine and cosine just equal √2, or sine, I should write it out. Sine of pi over 4 equals cosine of pi over 4 equals √2 over 2. So the velocity at t equals pi over 4 is going to be, let's see, -3 √2 over 2, 3 √2 over 2. Acceleration is going to be negative, or I should say v equals a equals 3 Speed will just be the magnitude of velocity. So that'll be, let's see, square root of, let's see, be 2 times 3 root 2 over 2 squared, which I believe that's just going to be 3. And then direction is just going to be velocity over the magnitude of velocity, which is just going to be negative root 2 over 2 root 2 over 2. Okay, so we need to find the equation of the tangent where t equals -1. So the first thing we need to say here is that just what the equation of a tangent looks like. So that's going to be taken from point slope form, which is just y minus b equals mx minus a, and then we need to find b, a, and m, which is a comma b is the point we're going from, and then m, of course, is the slope. So let's start with the point we're going from, which is r of -1, and that's just going to be let's see, -2 minus 3i plus -1 plus 12j, or -5i plus 11j. And then we need to find the velocity function, which is just the derivative of position, or 6t squared minus 6ti plus 3t squared minus 12j. And then we want to find the velocity at t equals 1. So, -1. So velocity of -1 is going to equal 6 plus 6i plus 3 minus 12j, or 12i minus 9j. But then we don't just need the velocity, we actually need the slope of movement, or the slope of the velocity. So m is going to equal its rise over run, so the y component over the x component, or -9/12 or -3/4. And so now that we have that slope, we can just plug it into our point slope form and say that y, we have this point up here as well, which is -5, 11, equals a comma b. So we can say y minus 11 equals -3/4 x plus 5. And that is our equation for the tangent. And now we have the second part of this, which is we need to find the coordinates of each point on the path where the horizontal component of velocity is 0. So, of course, to find where the velocity of 0, we need to know the velocity, which we have from above. So we can say that velocity equals 6t squared minus 6ti plus 3t squared minus 12j. And then from that, because we need to find where the horizontal component is 0, we only are concerned about this I term. So we just set that equal to 0, 6t squared minus 6t equals 0. T minus 1 equals 0, and then we get that t equals 0 and 1. And now that we have those two times where the velocity is 0, we just need to find the coordinates of both of those. So we can do r of 0 equals, that's just going to be 0i plus 0j, or 0, 0, and then r of 1 is going to be, let's see, 2 minus 3i plus 1 minus 12j, which is just going to be -1, -11. And that is where the velocity is 0. All right, sweet.